Good morning, one and all. I welcome to the Day 5 Faculty Development Program on Blockchain Technology being organized by Bangalore Institute of Technology in association with the AICT Training and Learning Academy. I thank Dr. Pavan Kumar for joining us today. I welcome you, sir. Giving an introduction to Dr. Pavan Kumar. But Dr. Pavan Kumar is an assistant professor with the Department of Computer Science and Engineering at the Indian Institute of Information Technology, Dharwad, Karnataka. It is an institution of national importance. He did his PhD from Bengaluru Institute of Technology, Vellore. His research interests include coding theory, data communication, formal languages and automata theory, cryptography, and applied mathematics. I thank you for accepting our invitation, sir. I heartily welcome you to this session.
Yeah. Thank you, ma'am. Thank you for inviting me, and also good morning all the participants for joining us in the morning, and also that too on the last day of the workshop. So, what I will do is I will just give a brief on how exactly the error correcting codes will work, and then I'll go through the blockchain, how that can be applied to the blockchain. Right. So all of you on these all 4 days, you might have seen how exactly these blockchains will work, how the smart contract will work. So you can help me out in understanding how these smart contract aspects can work in blockchain. So just let me share my screen, and also for the benefits of the participants, I'll just turn off the screen so that the bandwidth will be saved. Right. Just let me share the screen. Right. Yeah, is the screen is visible?
Not fully visible. I think since it's a PDF format.
One second. Can you see the screen now?
Yes, sir, it's visible.
It's in full screen, right?
Yes, full screen.
Yeah, okay. So if you have any, in between, if you get any doubt or something, just let me know so that we can see what can be, I will try to answer them if I know the answer, right? So shall we start with the presentation?
Yes, sir, please.
Yeah, sure. So, to give a brief on our institute, ours is Indian Institute of Information Technology, Dharwad. It has been set up by the Ministry of Education, earlier which was called as the Ministry of Human Resource Development. We offer BTech programs in computer science and engineering, and electronics and communication engineering. And recently we have started with data science and artificial intelligence as well. Apart from that, we do offer PhD programs in almost all the relevant disciplines of information technology, starting from artificial intelligence to even theoretical subjects like theoretical computer science. We do have programs. So, and also we offer internship for the BTech and MTech students, wherein if they can do their internship projects or the final year projects, we do that as well. Okay, and we are situated near to Dharwad. So for coming to the talk today, what I will do is I will give an brief introduction what exactly these error correcting codes are and how the coding theory will work, and then how this encoding and decoding mechanism works, and then how this there is a special kind of graphs called as trellis graphs, how this the trellis graphs can be used, and then we will see briefly what is distributed error correcting codes and how exactly they are being used, and then we'll descend to how this coding theory can be used for the blockchain. Right. So now, till now, you might have seen how exactly we will write the smart contract and how do we place them in the blocks with the help of the hashes and other cryptographic primitives. So you might have seen proof of stake, proof of work, and all those concepts related to the blockchain. Right. In the proof of work and proof of stake, how these miners will help to add some data into the blocks, right? Like this, everything will be added to the block. But what will happen to the size of the blocks? Do we really require to keep a consensus protocol and keep all those in intact? Is it really been required? Those things we will just discuss as we go along the course, and we will see how we can make some difference by using the error correcting codes. So before I start with this, one more thing I would like to tell you is now you keep we all use Gmail for our applications, right? So like whenever we save our data on the Gmail, the industry practices, the Gmail in turn saves that data at 3 locations, so that if any one of these locations fails, at least you can be routed to the other 2 locations, and then you can get back the data. That means like you say if you store 10 GB of data in your Gmail, the Google in turn stores 30 GB of data at 3 different places, right? You can now imagine how much enormous space is required even for this blockchain, because it has to host all the data which has been stored by the users. On top of it, it has to maintain all the records at all the places which are in consensus with that. And in turn, it has to even keep a copy of that, so that if any one of the nodes will get damaged or whatever due to natural calamities or deliberately if something has been going down, in all such cases it should come in hand, right? So you can see, like, now can we use this coding theory can for reducing that requirement of the space, right? For example, if you take Facebook, by using the coding theory, you can see in the recent press release, what it says is like you can reduce the storage requirement by 1.5 times by using the error correcting codes intelligently. Not only the Facebook is using that, Microsoft is using their own, and also the different features or the industry leaders are using them for doing it. Like for example, if you see the Amazon movies, right, that will be streamed, all those will use the coding theory in turn, so that they can reduce their storage requirements, but at the same time efficiently give the content what the users are looking for. So once I will give just an overview of all these things, and then we will see what are the research trends and applications which you can pursue if you're interested in further, right? So is my voice and slides are clearly visible and also audible? Just let me
Yes,
know.
sir.
Yeah.
Yes.
Okay, fine. So like to start with, there are 3 reasons in the literature to to encode the data that is to be transmitted or stored. That means like when you have some data, you will encode it, or for some reason you will do it, right? There are 3 main reasons for doing so. One is for efficiency, that is for information theoretically. What we will do is, if there is any redundancy in the data, if there is any redundancy, we will try to remove them and we will save them efficiently. And the other thing is for error correction and detection. Like if you are transmitting some packets over the network or through some which are miles apart to the two devices, if there are any errors in the transmission, that has to be corrected, that have to be corrected on their own without any manual intervention. For example, like if you're sending something from the space, like the satellite has taken some picture of some other planets, and if it is sending to the earth, right, we cannot ask the satellite to send it again because the picture clarity is not good, because that have to be sent in such a manner such that even if the part of the signal has been corrupted, we should be able to reconstruct that and get back it, right? And the other main reason for doing so is for secrecy or authentication. This is mainly for the cryptographic principle, wherein we will encrypt the data. Here we don't use the term encode data, but we will use the encrypt the data, so that we will get a ciphertext which is not readable, right? If you take a typical digital communication scenario, what will be done is like the information which is to be transmitted will be first source encoded, so that if any redundancy is there, it will be removed, and then it will be encrypted, and then suitable error correcting codes are used for the channel on which it will be transmitted. And before transmitting over the channel, suitable modulation techniques will be used at the sender side. Similarly, at the receiver side, it will be first demodulated, and then suitable error control decoding techniques will be used, whereas the encoding techniques were used at the sender side. And then further, it will be decrypted by using any of the cryptographic principles which we have used here. Here, the term of public key or private key crypto system has been used, right? And then again, we will do the source decoding and we will get back the data. This is how the digital communication scenario works, whereas we are using it on the WhatsApp, or we are streaming the videos, or like if you're communicating over the phone, all this will make use of this as the skeleton. Without this model, it will not work, right? So how this error detection and correction will work. In these 3 aspects, I will just concentrate on the coding theoretic aspects. Like if anything is transmitted over the channel, that is can be any medium, like through the mobile network or to the satellite communication or any other network. Like if it has been transmitted, there will be certainly amount of error is been introduced by the channel itself. So how do we correct those? That we will be seeing, right? So to give just brief on error detection or error correction, so these redundancy bits are added to the message in a predefined order at the source itself. So if you are from computer science background, you can think this as a mapping. C, that is a code, is a mapping from sigma power k to the sigma power n, where k is the length of the information or the message. Like I'm not talking about the what is the size of the information. I'm just talking about the length of the information or the message that is been encoded into the n bits. That is, length is the n over here, and significantly this k is less than n, and sigma is the set of alphabets over which it has been defined. Since sigma in a digital communication scenario will be zeros and ones. So we are defining a string of zeros and ones of length k, and we will be mapping it to the of the length n, and the length n is certainly greater than the length of the k. And also one more important aspect, if you want to observe over here in the length of the k and n, in the case of the error correcting codes, we will use this different lengths of k and n. But if we use in the case of cryptography, the lengths will remain the same, because we are not doing a mapping of these domains. What we will do in that case is we will just take one character from this side, from a like what is a domain, and we'll map it to the codomain. But whereas in the case of error correcting codes, we will do it in a different way. And these coding schemes can either be linear or non-linear. So these linear codes are defined over generally the algebraic structures, which are called as vector spaces, whereas non-linear codes are defined over the simple groups. Right. So to give the important overview of this coding theory, it will include two functions. One is encoding and the decoding. Encoding will be done at the source, and decoding will be done at the sink or the receiver. Encoding will be done at the sender, and the decoding will be done at the receiver. And this encoding function E will be given as a map from sigma power k to the sigma power n, where sigma power k is a set of message words, are also called as the message space, whereas sigma power n is a set of encoded words, are also called as the code word space or the set of code words. And similarly, the decoding function, like now we have encoded, that's fine. At the receiver, it has to decode it, right? So this decoding function is given as again a map from sigma power n to sigma power k, where sigma power n is the code word space and sigma power k is the message space. Now, using the decoding function D, the received code word, that is sigma power n, has been whatever been code word is received at the receiver, right? It has to be mapped back to the actual word m, which has been transmitted, right, on the channel. But in the case of that is an idealistic scenario. But if you have any of the adversaries in the channel or in the noise, if you assume that as a eta is a noise that also belongs to the same alphabet, then the decoding function has to intelligently decode the message what has been present, so that it has to map or it has to decode the sigma per n plus eta, that is with the added noise, whatever been corrupted or whatever been received has to map to the actual message. So decoding function has to map the received code words to the corresponding words, nullifying whatever the effect this eta will introduce to the message. And this error correction and decoding will be performed in three ways. One is by using the algebraic decoding, and the other is probabilistic decoding, and then the graph decoding. In the algebraic decoding, what it will do is it will use the underlying algebraic structure properties. Like suppose say if you are using a field, or if you are using any ring, or any of those ring properties or field properties, we will try to decode and correct the errors. For example, if you take the TV communication, right, that will extensively use this Reed-Solomon codes. So that are defined over a Galois field or Galois field, we call that. So using that, it will do the algebraic decoding. But another challenge with the algebraic decoding is it requires the channel output to be quantized before the start of the decoding. So it requires the channel output to be quantized before the start of the decoding. Whereas in the case of the probabilistic decoding, it will use a maximum likelihood decoder or a maximum a posteriori algorithm to decode whatever been received at the receiver. See, all these techniques, if you observe carefully, the challenge is in the decoding. because like it has to correct all the errors that are being introduced into the channel or due to any other reason, and then it has to be corrected. So another way is graph decoding. What are the problems with the algebraic decoding was the channel output has to be quantized before the start of the decoding. So another one of the ways what they thought is, okay, graph decoding can be done. What they will do is these code words will be represented by using a suitable graph, and a maximum likelihood graph decoder will decode based on the paths which are there in the graph. One of the popular methods which has been used is the maximum likelihood Viterbi graph decoder. We will discuss this shortly, what exactly this graph decoding will do, and then we will not touch into algebraic decoding and probabilistic decoding. I'll just take with the example of the graph decoding, and then how this graph decoding will work, and how this Viterbi algorithm will work, and then how this will be applied onto the blockchain to achieve our objectives. Okay. To set the stage for understanding this, there is a concept called as distance between two code words. Like suppose say there exist two code words C1 and C2, and that belongs to the same encoded function sigma power n. Then the distance between them is defined as the number of positions at which the C1 and C2 will differ. That means in one of the cases it may be 0 at one particular bit, and the another particular bit it is 1. Then the distance is taken as 1. We will see that with an example, just the definition. That is the number of positions in C1 and C2 at which the corresponding symbols are different. Then the concept is called as the minimum distance. Suppose say there are two code words are there. Now, or the encoded words are there. How do we define the minimum distance? So if you compute this distance between all the pairs of the code words that exist for a particular family of the code, the minimum distance is defined as the minimum of the distance between any two code words that belongs to this code book or the code family. That means like if you take an encoded code words EX and EY, any two encoded code words, then what is the minimum distance between them? That is called as the minimum distance of the code. So this minimum distance is playing a very crucial role over here in the coding theory, and this error correction and detection parameters will give how many errors a code can correct and how many errors the code can detect. See, the code detection is like error detection is, it can say that, okay, there is some error in the message that has been received. That is the concept of error detection. Error correction is out of the messages which have been received, how many bits I can correct them. That is called as error correction. So this is the difference between the error correction and then the error detection. Now suppose say I will take delta as the minimum distance which I computed by the method which I told you previously. If delta is the minimum distance of the code, then all the errors of weight less than or equal to delta minus 1 can be detected, and all the errors of less than or equal to half times delta minus 1 can be corrected. We will see like with an example how many bits are corrected, how many bits are been detected that they are received in error, right? And also this is not the regular one like you may be studied about the CRC and all those things. It is slightly different from those CRC, but it will be like helpful to understand. So out of the messages received, you can detect up to delta minus 1 errors, and you can correct up to half times delta minus 1 errors. Okay, and this while designing the new codes, a trade-off need to be achieved among these three parameters, where n is called as the length of the code word as we have seen previously, and k is the length of the message, and d is the distance parameter, that is the minimum distance between any two code words that are present to that family, and this q is the length of the alphabet or the number of not the length, it is the number of alphabets they are present in the sigma. Like sigma is the alphabet, right? So number of symbols, sorry, not the number of alphabets here, number of symbols present in the alphabet is given by the q. If it is a binary code, then this will be 0 and 1. If it is a ternary code, it depends on how do you define it. See, like mathematicians, when they have defined this coding theory, they have even gone to the non-binary codes as well. But as for communication engineers and computer science engineers, we are concerned only about the digital aspect. So we have considered only the 0, 1 as the alphabet. So by default, this Q will be 2 for most of the digital communication scenarios which we are going to consider. So N is the length of the code word, K is the length of the message word, and D is the minimum distance. So having said that, what is an error correcting code, right? So an error correcting code is defined something like this. So an error correcting code or a block code C, which is indicated by this symbol of length N over a finite alphabet sigma, is a subset of sigma power N. So whatever code is defined as C as a subset of sigma power N, you can see. And if sigma is supposed as field, that is the whatever the symbols you have chosen, if it forms a field, right? And if C is a subspace of that sigma n, then C is said to be a linear code. And the elements of that are present in this C are called as the code words in C. So all this collection of these code words are sometimes is called as a code book. Then one of the example of simple codes are two there. One is the triple repetition code and the other is the double repetition code. How it works? So this is N and this is K, for example. If you take now this M is like a single digit, or you want to send a 1. So instead of sending a single 1, what I will do is I will send it thrice. So at the receiver side, if I receive like 2 ones then and 1 0, then I will understand that okay, the sender has sent 3 ones, but I have received only 2. So one bit might have been flipped, or it has been received in error. So I will go for the majority decoding, and then I will see that okay, it has to be 3 ones. But there is a catch in this method. If I receive 2 zeros and then only a single one, then I will make a mistake and say that okay, the sender has sent the 3 zeros and he has not sent the 3 ones, right? So that is the what you call as a decoding failure. So decoding failure is one wherein we will fail to decode it to the correct message which has been transmitted. So in the double repetition code, we will say that okay, instead of sending a single one, we will send 2 times ones, so that at the receiver we will understand that okay, it has been sent once, so it will check for any discrepancy is there and it will correct. But even though they are not very efficient methods, so we have to construct some efficient methods that will try to identify which are the correct messages that has been transmitted, right? So for doing that, there is something called as a linear code. They use something called as a generator matrix. So how do we define this generator matrix? This generator matrix is defined such that the first part of this generator matrix will be an identity matrix, and this second part will be chosen carefully such that it will help us in error correction. So there are various methods for selecting that I will not go into detail, but for the understanding sake, just understand that there will be some generator matrix. It will be in this order, wherein the first part will have this identity matrix, and then the second part will have this A, wherein the entries of this is given by Aij, where I and J represents the particular row and then the column, right? And then having said that, like how do the parity check matrix is been defined from a given generator matrix? So from a given generator matrix, this parity check matrix is given such that it will be taken into such a way, if we will take the A transpose and then we will take the identity matrix. We will see an example and we will see how we can correct the errors that has been received over the communication channel, right? So one of the decoding schemes that will uses the simple matrix concept, and I will just give you an overview of how this works. So this will be able to correct only one bit that has been received in error. So this decoding scheme will work only if the received parity check matrix or the generator parity check matrix does not contain a column of zeros, and the no two columns of this parity check matrix are identical, right? When these two conditions are satisfied, then only this algorithm will work. These are the method how this algorithm will work to compute the syndrome and then how to correct that syndrome. Syndrome is the place where exactly the error is been located. Okay, we'll now see an example and we will try to do this and understand how this error correction codes will work. Now suppose an encoding function is given as E that is mapped from Z2 to Z2 itself, that is from a that is having 2 elements 0 and 1, and it is mapped onto another group that is on Z2 power 2 is given by this generator matrix. If you observe this generator matrix carefully, the first part, the first two columns are the identity matrix, and the remaining part will form the A matrix A. Now first we will try to do which are the code words are possible for this code, and then what is the error correction and error detection capacity of this code, and then what is the associated parity check matrix, and then how we can use this parity check matrix to correct the errors, right? And I know that Z2 will consist of 2 bits, that is 0 and 1, and the matrix A has been given over here. So how I will do the encoding is, I will assume that which are the messages possible with the 2 bits, because here I am giving that only 2 bits are been communicated, right? So to understand that, like, which are the possibilities? 0, 0, 0, 1, 1, 0, and 1, 1. So how do I encode this message? I will multiply that with the generator matrix. So message is 0, 1, that I am multiplying with the generator matrix which has been given. Then I will get 0, 1, 0, 1, 1 as the encoded word, or I will get the encoded message. Similarly, if you compute for 0, 0, 0, 1, 1, 0, and 1, 1, then we will obtain these as the code words. And from the code words, if you can compare them, like if you compare these two, right, how the distance between these two codes will work. First, we'll see that concept. So here there are 5 bits or 0. Here the second bit, third bit, and second bit, fourth bit, and fifth bit are ones. So if you compare these two at 3 positions, these 3 bits are in differ. So the distance between these two code words is 3. Similarly, about this one and this one, if you compare 10110 and 01011, if you see these two, it is differing at the first position, second position, and then the third position, and then the last position. So at 4 places it has been differing. So if you compare all these, then we will get something called as a minimum distance. That means at least it is the minimum places at which these 3 bits are differing is 3. So it can detect. So now my delta is 3. So I can understand that it can detect 2 error bits and it can correct 1 bit error, right? And then from how do we construct a parity check matrix from this G which has been obtained, right? So first time what I will do with that is, I will take the A transpose, whatever been given as the matrix A, I will just take the transpose of this, that will form 1, 0, 1, 1, and 0, 1. And then I will take an identity matrix suitable to fill this gap of 3 places. Like, so I will take a 3 cross 3 identity matrix. So if you observe this, the first part will become the A transpose and the later part will become the identity matrix. Now, how do I correct the errors which has been received? Assume that the 11101 has been received. So that is called as the syndrome of the R. Like the syndrome, how it is calculated. So I will take the transpose of the received message and I will multiply that with the parity check matrix. So parity check matrix is given as this one. So if I multiply with the transpose of the message which has been received, then I will see that the resultant is triple zeros. So the challenge over here is when we are receiving this resultant as 0, it is understood that there are no errors in the transmission. So there are no error has been introduced by the channel when it was transmitted. So I will take another example wherein 11011 was transmitted. Then if I calculate in the same method multiplying with the parity check matrix, what I can see over here is it is 110. If you multiply this, I will get a result as 110. Then I will compare which column of the parity check matrix is 110. So I will see that the first column of the parity check matrix is 110. So by this I will understand that, okay, out of the message which has been transmitted, the first bit is received in error. So I need to change the first bit. So the message which was transmitted to be 01011, but by mistake it has been received as 11011. So if I see 01, like 01011 was the message that has to be transmitted. So I will change this first position and I will take that message as 01011, and then the message which was supposed to be transmitted was 01. This is how I correct the error which has been received. So some of the popular codes which are there, which are more likely or lessly that works in the same principle, are the Reed-Solomon codes. See, this Reed-Solomon codes are the first family of the codes which are like extensively used in many communication applications. Till today, some of this white space communication, which call as the TV space and all those, will use the Reed-Solomon codes itself, and they're extensively even used in the Voyager space missions, wherein the photos or the photographs from the satellite were transmitted to the Earth from the extraterrestrial space. Similarly, Reed-Muller codes, Bose-Chaudhary, Hockingham codes, and then the turbo codes. Probably you might have been using this turbo codes in day-to-day applications, right? Like if you see the CDMA mobile communication, or if you use this 4G communication, like by Geo phones, right? Like Geo, not phones, Geo network. Geo network, if you use, like you will be using a part of the turbo codes that has been extensively used over the long-term evolution networks, that is called as the LTE. Those LTE will make extensive use of this turbo codes. Similarly, there's low density parity check codes, fountain codes, even the TCP/IP model, which we are using extensively in the communication, right? They also use this fountain codes. They are also called as the rateless codes. Okay, and the other family is concatenated codes. These concatenated codes are not particularly of any family. They are taking the two separate codes, like a Reed-Solomon codes and a Reed-Muller codes. We have come up with a new family that has the good features of both the codes. In some sense, you can say that the hybrid codes, but in a manner it is intelligently done. So we will see some of the concatenated codes. So this Fournier introduced this concatenated codes that were successfully used in the Voyager space mission of 1974. Like what they do is, like they had combined two families of the codes, so that even if any of the bits which has been received in error will be corrected by a mechanism, so that we need not ask the sender to send the information again. But even though these concatenated codes or the hybrid codes look very simple, in general it solved two fundamental problems in the coding theory or in the communication systems itself. One is proposed by the Shannon. I think you might have heard the name of the Claude Shannon, who is called as the father of the information theory. What he said is, like, to communicate with a rate less than, like you can achieve this reliable communication only if you communicate with a rate less than the channel capacity. And on the Hamming side, on the other hand, like R.W. Hamming, what he said is to correct the errors that occurs during transmissions. So, okay, I want to just talk about Hamming a little bit. Hamming has written a very good paper on you and your research. So, if you search in the Google, you will get it, right? Make some time to go through that article. It will really say how exactly you can future, or how you can really, foresee your career in research, and how you can devote your time, and how you can do some of the good research. So one day while working in a lab, what he thought is, like, okay, if the computers can correct themselves if any errors are there when the bits are stored in the magnetic tapes, right? Sometimes what happens is this magnetic tapes will, due to the material property, that will lose the information that is holding. So he was thinking, like, if the machine can correct themselves and recover the bit which has been lost, right? So that is where the Hamming codes came into picture, and he proposed that. So combining these two models of this coding theory has solved, actually the concatenated codes solved these two fundamental problems there in the communication, that is to reliably communicate with a capacity less than the, with a rate R less than the channel capacity, and correct the errors as well that occurs during the transmission. So next, coming to the codes on the graph, how do we use this codes on the graph? Like now we have seen how the error correcting codes have been constructed and how they are correcting the errors. Here what we will see is like how these codes can be represented over the graphs. So such graphs are called as trellises. So there are various scientists who have worked on this, but one of the definitions I have taken from is Chit-Sang and Sorkin. What they define is, so trellis for a block code, it can be given as an N is an edge labeled directed graph with something as a root vertex and something as a tour vertex. What you can see is the initial vertex and the end vertex, but these two will have the in degrees and the out degrees as 0. And then all the vertices can be reached from the root, and the goal can be reached from all the vertices. Yeah, goal vertex is also called as the tour vertex. Okay, I will see with an example. Just see this definition. And the number of edges that is traversed in passing from the root to the tour along any path is given as n, and this n is exactly equivalent to the code word which has been constructed. The set of n tuples obtained by reading of the edge labels encountered in traversing the path from root to the tour is the code word. So any code that is represented over the trellis is called as a trellis graph, and it is denoted by C of t. Anyways, that is the mathematical definition. So we will just try to see how we can use that for the error correcting codes, and then how do we take it to the blockchain, right? I will give a simple construction of a code over here that is done over the mathematical structures that are called as group. This let G1, G2, G3 be finite groups, and S be an abelian group with an identity element E, right? In such case, the kernel of the homomorphism mu is defined as a map from G1 cross G2 cross up to Gn, which is mapped to the abelian group yes, and such kind of a mapping, because like it is a subspace of a sequence space. If I take Cartesian product and the bits G1 to Gn, and if I take the homomorphism, right, that will form a kernel code where mu I is the homomorphisms defined from Gi to Gs. These homomorphisms can be defined as required for the channel or the application. So if you see this case Z2 cross Z3 cross Z2, and it is mapped to Z2. In this case, I will take this homomorphisms defined such that this mu1 is of 0 is 0. This I can define on my own. And if you take three groups, the Cartesian product of this thing is like Z2 can have the elements 0 and 1. Z3 can have the elements 0, 1 and 2. And Z2 can have the elements 0, 1. So which are the Cartesian products are possible with this is like 0, 0, 0, 0, 0, 1 and so on. This is like now from the homomorphism defined property, I will obtain these as kernel code. Okay, now this is also in form of error correcting codes, but the thing is only it can correct a 1-bit error. That's another thing. Like okay, like one more thing is there. This is an BLR test, Bloom, Ruby and Rubinfeld test. What exactly this test will do is, if you give an oracle access to an unknown functionality f, and there is a mapping from G to H, and if you take any xy randomly and independently from randomly at uniform from G, then if you perform a query on this such that, like if you take and if you carry out a function x plus y to find out f of x and f of y, and also compute f of x plus y, so it has to accept only if f of x plus f of y is equal to f of x plus y. That means if you take something from this x and y, and if you perform x plus y, that has to hold good even in this. So this is how the BLR linearity test is defined. Even though it is one of the tests, it has a lot of significance in cryptography and all those things. You can just Google it and you can find out more. So to talk about the trellis triplets for the kernel code, right? I was talking about the codes like trellis codes. So how these trellis codes are been used, or trellis has been used to represent the code. So this is just a simple algorithm to represent them. So if you see the previous codes which I have got, that is 000, 011, 021, 100, 111 and 121. So if you observe, like whatever the definition I have seen there, or I have given there, like this is the root vertex and this is the tour vertex, and all the paths from the root to the tour will form the code word. So if you observe here 000, 111 and 121, all these are the code words that are being indicated or represented over this graph. Similarly, if I can use an concatenated kernel code and define, like whatever the kernel code I have defined, I will take as an inner kernel and I will define something as an outer code. Then in such case, what will happen is the outer code, this parity checks, I will again add some of the additional bits to correct the errors. So this HIs can be chosen as applicable for the error correction, and the image of mu dash is defined as the outer code. So this is just the mathematical definitions. This concatenated kernel codes are the images of the elements of the kernel mu composition mu dash under the mu dash, right? Now if I add that parity check bits to the previously existing code by defining the new homomorphisms, I will get these as the concatenated kernel codes. But how do we define, or how do we represent them? So if you see this graph now, this entire graph will have all the code words starting from root to the tour. So if you see 1, 1, 1, 1 and 0, so this has been represented like 11100, right? 11100. This is one of the code words. See, like you cannot have an other way around. That means if something is there as from root to tour, and if that is not there in the code word, that is not possible. That is means it is one way. That means whatever the code words are there that are represented over the graph. If something is there in the graph, that need not be there in the code word. Okay. So that is how the thing is defined, and this follows some of the properties that proper, co-proper, and then bi-proper. Like what is in general, what the proper says is there will be an unique root vertex, and then whatever the edges that will start from these vertices will be labeled uniquely. That means if you see any of these vertices, you can see that this is 0, 1, 0, 1, all these are there. They are not having the same labels. And if you observe it, like if any automata theory or formal languages, the teachers are there or students are there, they can see over here that this is an equivalent to a minimal automata or minimal DSA, you can say, wherein you have a state which has been minimized, and you will have all the transitions. If you see this as the states, and these are the transitions, right? But in that case of the transitions, we don't consider more properties, but this can be viewed as a simple automata or a discrete state machine. We can take it, finite machine we can take. Similarly, there can be some properties like co-proper and bi-proper, which can be defined. What the co-proper says is, even if you change the direction of these edges, like then also it will not change the distinct label property. So if something is proper and co-proper, then it is called as bi-proper. Even though they are the mathematical definitions, they will be very much helpful on defining all these things. Similarly, there are one-to-one, observable, minimal, and all those properties. Now coming to this, what are the application of these codes, right? So like one of the things what we can see is like erasure coding. Like why this erasure coding is important is, now we are transmitting some data from one base station to the other station, or if you're having a communication for the ambulance, right? So if you send a signal for the ambulance to come to your place, by mistake, if it sends a reverse operation that don't come, everything is fine, then the ambulance will not come. So we should make sure that when you are using such critical applications, such as in vehicular ad hoc networks or in the rescue operations or in the control systems, we should make sure that there are no such operation failures from our side, so that it can result in a fatal situation. So one of the what I said, tools that can be used to make over such kind of a situation is called as a erasure coding. So erasure coding is just similar to the error correction codes which I discussed. What it means is the construction of the message M from any k out of the n packets received. That means, like, assume that these are the k packets that have been flooded over the network as n packets. Now, out of this n packets which I have received, if I select any k at random, I should be able to reconstruct the message that has been transmitted, right? So any k, like, see, I need not even bother about which of the k's I am picking. So any k I can pick and I can reconstruct the message. So this is called as the decentralized erasure coding, or also called as the distributed erasure coding. So I need not depend on only particular n packets. I can take, particular k packets. So I can select any k packets and get back the information from this n packet. So this is called as the distributed erasure coding. So distributed erasure coding problem in any networks refers to querying any k out of the n nodes in the network and obtaining sufficient information to reconstruct the original message from k nodes. Now assume that this is a sensor network. There are k sensor nodes are there. They are encoded and stored in a network of n nodes, such that if you take any k out of this n, you should be able to get back the message. Now think of this as a large computer network or a data center, wherein the information at the 10 nodes is stored at 25 nodes in an encoded format. So you can select any of the 10 among them, and then you can reconstruct. See, even this can be another advantage is, like, if some of these, if you assume this as a data center network, if some of these nodes get destroyed, or like they're low or whatever reason, I can query any k available things, and then I can get back the message. This is how the decentralized or distributed erasure coding method works. How we do it in mathematically is, like if you are getting a packet of data, we will multiply with the generator matrix, and then we will get the encoded packets. These encoded packets we will store at distributedly in the network. I should have these measures as k and n fixed, so that like whenever there is a requirement to reconstruct the data at one particular place, then I can take any other help of the other nodes in the network and do it. One of the examples I will give you over here. Assume that now this is the data center, like whatever the data is of the users is stored at these locations. Now assume that this one or two of the nodes in this data center go down, or like they got spoiled over a period of time. In such case, what to be done? So the rule is like I can access any k points and get back the message. So I need not even bother if couple of these data center nodes goes down, because I have the encoded packets. I can combine them and get back the message. So, and also how do we decode it? We will decode it in the similar way which we have seen previously, right? And also there is a concept that is called as a locality in this. So the locality is like, now suppose these are the right nodes wherein the encoded packets are being saved. The number of locations which we are accessing to get back the message, right? So this number can be even less than k. So if I'm able to get that with locations, suppose some r that is less than even k, then that is much more beneficial, because I need not even worry to access the k nodes, and then I can do it just by accessing the remaining. And there is another concept now. Like in this case, suppose this node has gone down, right? Then I can connect to these neighbor nodes which are there. Now I need to replace this, right? Like, because in future I may again require it. What I can do is I can reconstruct the data which is in encoded format stored at this place by accessing any other neighboring nodes. That is also been possible. Okay. And then there is a locality in the sense the number of nodes which are being accessed to recover the informations, right? And also in the decentralized erasure coding setup, a code C, which is a subset of this field, is said to have locality R if the symbols like which has been received, that has been X, can be recovered from a subset R, other symbols of the X, and this R is less than the K. Now we have seen what is the rate. Rate is defined as K by N, where K is the information and N is the length of the encoded word. And if you can come with an number R, which is even less than the K, so just by accessing the R nodes, I will be able to reconstruct the message that has been lost at the other nodes. And this D, the distance, is defined by N minus K minus this concept. Like if you are able to construct any code that follows these two parameters, they are called as optimal locally recoverable codes, right? Now, having said that background, how do we connect this to the blockchain? So we know that blockchain is a distributed system that builds consensus among the untrusted participants. The participants which are there in the network need not have any trust on each other, but still they can have a network and then communicate something and then store some data, agree upon some conditions, and get the results or get the work done what has been required, right? And it is also believed that the blockchain technique has the potential to revolutionize the digital world, because everything will be stored in a ledger which can be accessible, and at the same time it can be accountable. So Internet of Things connects billions of devices, and each of them generates and exchanges massive numbers of data. That number is massive in the sense like it may go up to the level of like what to say TBs or even more than that. How do we do this, right? How we can use the blockchain efficiently so that we can issues for such large IoT network need to be addressed. Something of them are collusion, confidentiality, integrity, and then the authentication. And one more point I want to stress at this point is blockchain is not the solution for everything. So it's not like an hammer and a nail problem. Like, so if you have a hammer, it doesn't mean that you should hit the nail wherever you get a chance to do so. right? So it has to be done carefully, whether first we need to analyze whether it requires a blockchain or not. Then only we need to do and go for the blockchain application, right? And this blockchain has many applications, like if you see, are like IoT networks, data storage, smart grids, right? But all of them rely on a central cloud service provider or a centralized server. Like now we can even make sure that such a centralized server is also not required for going for some of this application. Like what I will do is I will try to stick on to the IoT networks. Why I'm doing so is like we can have a small blockchain wherein you don't require a larger kind of a computation, whereas we do in the case of huge amounts of or large chunks of data. I'll have only a small amount of data. What I will do is like with the limited memories, whatever the devices are there, they are having the limited memory. So with them, how I can construct a blockchain so that I'll even get all the properties that a blockchain can have. So such chains, even many people call it as a light chain also, as a light chain also. But that anyway, like we will name as the blockchain itself, right? One premise of the blockchain systems is that each node needs to store the entire blockchain that leads to lack of storage resources. So as I told, everything has to be in a consensus protocol to add to the chain. So the nodes which are participating in the network has to have these resources stored at their nodes. So every time something has been added, so that this length will go on increase. Like I say that I want to add 10 GB of data or the transaction data to the chain, then if the 10 nodes are participating in this operation, then all these 10 nodes should have this kind of a data to store them, so that all of them have to store this 10 GB. Like don't think about only the 10 GB of the space, even how much network resources have to be transmitted over the channel, communication channel that leads to the what to say blockage to the other necessary resources. Like and also building another network parallelly is also a costly affair. So one of the solutions what you can do is, can I prune the old transaction data which has been present in the blockchain? Can I remove them and keep the only the freshly available things? But the challenge there is it will if you prune the old transactions, that will lead to some data unavailability. Suddenly say if I want to find the data which has happened 10 years back or 20 years back, then I may not have any connectivity to that or a link to that particular data. That may even lead to the data unavailability problem. So one thing is like, can we deploy the light nodes? So light nodes, what they will do is it will store only the block headers instead of the full blocks. But in such case of the light nodes, the challenge will be like, how do we authenticate this light nodes with the other thing? And also at the same time, like the number of what to say computations will increase, right? So whenever a new node or a full block has to join it, it has to have a copy of all the transactions that have happened in the network. So if I want to add a new node to the existing network also, it has to have all the data which is present in all the nodes and then run the consensus protocol. So one of the ways how we can address this is use an erasure code to encode and distribute each individual block, which reduces the required memory at each node. But how do you can do that, right? So what we can do is we can use a linear codes for encoding each block individually and assign each node only a small part of the code word. That means you can keep the part of the sum of the code word. So it can lead to the significant storage space reduction on the node memory requirement. And also when a new node joins the networks, what you can do is, instead of contacting all the nodes, collect some of the symbols from the neighboring nodes. So this you can connect to the point wherein like suppose if a node in the network has been destroyed, right? So in that case, like it will access the neighboring nodes and construct the message at that node. That point you can link over here. Instead of that, think in the other way. Like if a new node wants to join the network, it can collect some symbols from the neighboring nodes and it can reconstruct the message which has already been there or which can have a copy of, and conduct decoding in order of recovering the block. The challenges with this is requires larger computation, but conduct encoding in order to generate a new parity check symbol for this block, so that this block will take the memory which is less than the original node, but at the same time it requires a little more computation. That is fine, but it is significantly reducing the storage space requirement, because when a new node joins the blockchain, it simply requests some of the copies of the memory from neighboring nodes. Right now, we know that this ledger consists of the block, and each block is comprising of transactions and then a header. Right now, like these transactions and blocks are processed by the nodes, which are the, again in terms computational devices. There can be TVs, computers, and mobile phones, any embedded system that can be connected over a network. Like over some time back, there were some rumors saying that even some of the which are smart TVs connected to the internet are also doing the job of this mining, which you have discussed over the last 4 days. Like how do these miners will take some task and then divide it and all those things. Right. So what can be proposed is two categories of nodes. One is the full nodes and then the light nodes. This light nodes will have only the headers, and the full nodes will have the copy of the entire transactions. This, as I mentioned before, this full nodes store the entire blockchain, and the light nodes save only the block headers. So if anything is required, this light nodes will access to these full nodes and get the details of the transactions. And each transaction is created and then digitally signed by a node. So for instance, I will take an example, like a payment is made from node A to the node B, and it has been signed by node A, then it is broadcasted to all the nodes over the blockchain network, so that the full node can do the mining. Right. So mining consists of, as you have seen, putting several transactions together into a block and conducting some computational protocol. Right. So each full blocks which are already present, or you can say that the nodes which are present, they can verify whether the new block was formed correctly or not. That means all the transactions are valid or not. If the block is valid, then each full node includes it in the ledger. Right. If it is not valid, then it will be discarded. So the block header of or like this you have already seen, right? The block header of a block, what are the things it will consist of? Version, timestamp, and hash of the previous block header, and then the Merkle root, and what is the current target, and then the nonce. Right? This full blocks, what it will do is it will search for a nonce for the block header such that this inequality holds. This current target has to be set very high such that even the miners will find it difficult to compute it unless they have the huge computation power. So this inequality should hold so that it will give the, what to say, required strength for the challengers or the miners. And this the newly generated block will be comprised of the block header and then the selected transactions. Right. So once these full nodes will created, will broadcast this created blocks over the network. When it arrives at a new block, then it will again verify using a predefined set of rules if the block is verified by a few blocks and then added to their chain. If it is not verified by some blocks, then such nodes which has been verified and added to the blocks will be precluded. That means they will not be considered in the further computation. So it is very important to have the new blocks to be verified or by all the existing people in the network, right? And the blocks are linked together to form a chain to form the proof of work, right? So this blockchain, like what you can see from here is this blockchain has a huge redundancy, since each full nodes keep the entire set of these transactions and all the records which has been required, and the multiple copies of the same blockchain is stored in the network. Like multiple copies means, like, okay, one of the things is we need to keep the node intact, that is the first thing, and the second thing is like you need to keep the copies of the same, so that even if one of the copies goes down, like the miner or the, what to say, the owner of the full block can replicate the same thing at the other, and then he can get back. So just think, like if a full node is of the petabytes memory, then the owner of that block who is maintaining it, who will get a reward, right? So how much effort he has to put to store that petabyte of memory. So can this coding theory can help at this position, right? So assume that I'll give an example how we can use it. Assume that the total number of nodes in the blockchain is n, and these nodes are labeled distinctly. The indices can be assigned to nodes accordingly. They are joining the network, so that we can keep this in intact with the error correcting codes. And these the indices which are being assigned according to the blockchain joining timestamps will be there, right? The assumed blocks are in the ledger or enumerated by the integers, and then like each integer when a block has been added, they're enumeratedly joined. Like suppose say if this is the time at which one of the block is joining, the next consecutive block will join at the next time instance. Similarly, it will go on, where m is the index of the group. Like if you can make it as a group, then how we can store it, right? So if you see this block, it will be similar to a linear code over the finite field that encodes this t symbols, right? T symbols into n symbols, and it will store with the help of a code as an n comma t code. Okay, and this will be an systematic code wherein the first few blocks or the first few items or the bits in a code will represent the message, and the remaining bits will maintain the parity. So the same thing in the systematic encoding, wherein the first few copies will have the message, and then what has been required as the parity to reconstruct them will be used. Similarly, like in the entire network, there can be many blocks of such will be present. So what we will do is we will group them, and then when suppose say when group 1 goes down, we can contact whatever there in this neighborhood, and then we can construct the message at the group 1. So similarly, like what we can do is this whatever the messages are there, right? This KT symbols or whatever is there over here, like it can be given in the term of a matrix similar to the A matrix which we have seen previously. And then the systematic encoder to encode the each row in this matrix. So with the help of a like a data word, so it will result in the matrix of this format, which is the code word or which is in the encoded format. So like if you take one of the example for doing so, assume that one of the nodes wants to construct one of the messages that has been there. Like now this 4 is requiring to construct, like now we need to assume that these are locations at which these are not available. I want to construct the message at G2. So what it will do at first is it will request its neighbors, that is 8th node. Assume that there are 10 nodes in the network, and it will ask the 8th node to give some resources, and I will try to compute the V dash. So it will request 8, but it will fail to do so again. So again, it will try to enlarge it by accessing the others one, like 5 and 9, the nodes 5 and 9, and it will try to encode. Still, few more symbols will be missing. So it will take the 10th one, and it will try to reconstruct. This process will continue till we are able to compute this V dash which we require it. So now assume that these are all the nodes which are present in the network. If one of these nodes is missed at the location 4, then it can access what is there in the neighborhood that has a component similar to this 4, and it can go on expanding so that it will get the desired block. So if the desired block is lost, like 6 is lost over here, now I want to construct the 6 with the help of block number 6 with the help of the remaining nodes. One thing you can notice over here is it requires the huge computation and also the transfer of the messages from the remaining blocks, right? So one of the solutions can be given that is by using the Tanner graph. This Tanner graph will have something called as check nodes and then the variable nodes. These are the variable nodes and these are the check nodes. And this, if you see that the rows represents this check nodes, and then this label, like whatever is here, will represent the column. And if there is a connection between these two from a check node and to the variable node, that corresponding entries are given over here in the matrix. So this is one of the graph representations, like a Tanner graph similar to the trellis. So, and this uses the low density parity check codes, wherein the number of the rows will have the number of zeros more than the symbols. They are called as the low density parity check codes. And this is one of the low density parity check codes which has been introduced by Gallagher somewhere in the 1960s. If you get a time to see this Robert Gallagher's paper on tunnel graph, you will be able to understand this. But just for timing, just understand that these are the tunnel graphs and this is how they are represented. Now, like in this case, what happens is that in this case, like I require the resources from the neighboring blocks to reconstruct the message, right? So often, like what will happen is we don't require those many to do so. So what I will do is I have divided this into groups, right? I can take the resources from the particular group itself and then I will reconstruct instead of asking all the things which are there in the network. So I'm one side I'm reducing the network load and on the other side I'm reducing the storage requirement as well. So those two things are being compromised where, like one thing is like we are reducing the storage space requirement and also the how much of the message is been transmitted over the network. Like if you see this, like suppose if one of these blocks will go down, then instead of taking the resources from the other groups, I will just take the remaining things from this group itself and then construct. But the challenge here is like while constructing this kind of a chain, we should make sure that like when I'm constructing this, okay, I should construct in such a way that it should contain the encoded packets from the entire network, so that even if it goes down, instead of accessing all the nodes in the network, I can access only this portion and get back the message. That is how it will work. So like you can use this that mathematical concept can be given in terms of word. What I will do is like once you have in the matrix form, you can use all the Gaussian elimination methods, and then like you can get an systematic form of this type, and we can get a generator matrix, and then we can encode them and keep the data. So when one of the like nodes goes down, right, when they are constructed independently, we can only access those particular nodes and then get back the data instead of accessing the entire network. This is what the concept how this blockchain can be used, this coding theory can be used to reconstruct the data at the blocks, right? And also like this will be like now you can think this concept of this encoding is similar to your matrix multiplication. What you can think is, okay, packets has been encoded and kept at different locations. That's fine. If one of them goes down or if one of them have to join newly to the network, then it will take the packets from the neighbors which are present, then it will have its own full capacity. Once that been full capacity is grown, then it can communicate to all the members saying that, okay, I am joining to the network, please endorse me. So that all the remaining nodes in the network, like similar to the blockchain protocols, they can endorse that node and that node can become the part of the entire network. Like I'm just by this I'm saving the network parameters and as well as the storage parameters, right? So what are the advantages of doing so? One is data availability, and also we can identify the malicious nodes because no one can pretend saying that I am a legitimate nodes, provide me the resources. That is one thing. And also it can avoid this replay attack. Why? Because replay attack is like, okay, now I have requested at one particular time slot to join the network, but if I keep those records and in the future if I want to join, because I'm having the timestamp, right, I cannot do that. So replay attack has been ruled out. And also at the same time, as I told before, this storage cost can also be reduced by reducing the number of transactions because I'm saving this in the form of the encoded packets. But having said that, what are the challenges that do arise by this scenario, right? So one is the verification criteria. When this new node joins to the group, if that small group, which I was mentioning over here in this slide, this small group will consist of all the, what to say, like non-legitimate nodes or the intruders, then there may be a challenge that even if a legitimate nodes ask for the resources, then they can be misguided. So this one of the problem one can work on how this verification has been done. And also these fake transactions can be identified. Like can we have some fake transaction criteria, any other suitable mechanism within this small group, so that if any one of the imposter or like what to say an intruder try to say that I am an legitimate person, add me to the network, then if the group is compromised itself, then they can add the new node itself. So unless and until it has been broadcasted to the entire network, it is not possible to identify such fake transactions. How do we do that, right? And then the verification nodes selection, like now verify, I need to do the verification, right? Now, how do I select these things intelligently so that I can, the established methods like proof of work or proof of concept, how do I use them efficiently so that this verification task will be done at a limited amount of time? And next is the block distribution. Now, how do we distribute this new block over the entire network? Because like all the networks components should be in consensus, right? So how do we achieve that? Right, that has also been one of the problems one can look into. And then the requirement on the communication cost, right? Like now all these resources are, even though we say that that requires, okay, blockchain, but at the same time, how much is the communication cost in sending the information from one node to the other? Is it really worth of it? That, or like how do we reduce that further so that we can have limited communication between these full nodes, right? That is what this communication cost is. And also in general, what are the research trends are there, right? So what we can think is like, can we construct new algebraic structures that with increased error correction capability? Like now we have seen the code will be constructed as N, K, and D. Now can I construct a new code such that, like, okay, whatever the message is there, that will be correctly decoded to the correct message instead of reducing the number of computations required for correcting them? Because we know that this computation over the field is little bit expensive, because if you are someone is working on cryptography, you can understand that, right? So like how you can do that, that you can think of. And also this cryptography based coding based cryptography and secure computation, like can we use this coding theory for cryptography, and can we do any kind of homomorphic cryptographic scheme, and all those things we can just verify and check out whether this is a feasible option to do coding based cryptography and then do secure computation in the blockchain itself, instead of going like, because some of the resources are exposed in this case. So without exposing, can we use something called as homomorphic encryption scheme? Similar to that, can I have some other technique, right? So that can be used so that I can verify such things. And then how we can use this coding theory for the storage system? Like a lot of research has been done by many people for this coding theory for storage systems, but still space is there wherein you can propose new storage systems so that it can be efficiently stored and then efficiently the information has been retrieved. Like for example, as I told, Facebook and all this, the Netflix and Amazon are massively what to say, investing on this coding theory aspect, because like instead of storing the data at 10 petabytes data in 30 petabytes, instead of that, can we reduce it? Okay, I can encode the data of 10 petabytes and can I store it a location at 20 petabytes, so that if anything is required, I can decode and then get back. So this computation cost is lesser than the storage system cost. So we can work on such thing. And another is the coding for the light blockchain. Can we do something on the blockchain so that this whatever the huge requirement can be reduced, still keeping all the ecosystem provided by the blockchain? So that is the light blockchain concept. And then the coded caching, like now you will have the huge databases and all those full nodes, right? When we are sending on to the network, like some of the transactions are frequently being accessed by the people to verify, or by the other nodes. So can we use the coding theory over there? So coded caching can be done so that even still you can improve the on the communication cost side. So these are all the some of the things, and these are the references I used for this one. I will share with the coordinator Bhargavi ma'am, and she will share with you. So you can refer to this, and you can write back to me like if you have any doubt in all this aspect. So this now I'm open to the question. If you are having any questions, you can please let me know.
Yeah, the participants can unmute themselves and ask questions if you have any, please. Sir, I guess there are no questions from the participants.
Okay, that's fine. Yeah.
Yeah.
Thanks. Hopefully, like if some are interested in this work, then it will be really helpful. And thank you for all your patient listening. Okay. Thank you.
There is one question now, sir, actually, by Mr. Navneet saying, can we compress the blockchain data to reduce the storage?
Yes, that's what the entire concept
Right.
of this talk, right? Like how we can compress this so that we can reduce this storage requirement. Like now, if you can store this data at the n nodes at only this k nodes, right? So if you want to mine or do some transactions, we can do it only by accessing only those k. We need not even try about the entire thing.
Hello, sir. It's Navneet here.
Yeah, tell me.
Sir, what I'm saying is like, can we make some particular technique like in machine learning, we have a lot of compression algorithms to compress the entire big files to a small, very small size, like a 1 GB of file into 1 MB, something like this. Instead of downloading the
You can,
entire,
yeah, right. I got it. Like you are trying to say that, like, can we use eigenvalue, eigenvector kind of a thing, or PCA kind of a thing, right? Principal
yes,
component analysis.
yeah,
Can we
yeah,
do? Yeah, like we can try that by information theoretically. You can try that. Many have not tried it. So information theoretic tool, like how much you can compress still without losing on the principles of the blockchain, you can always try. For that, you need to understand the nature of the blockchain and try to see how is theory can be used over here. There is a beautiful concept on information theory, which was led after this Shannon's work on information theory and the seminal paper in 1948. So you can, like many people now also, they are working how this can be done. So you can use those principle and you can check it.
Okay. Thank you, sir. Thank you.
Yeah.
Sir, we have one more question by Ms. Radha Senthil Kumar.
Yeah.
Can we apply our own encryption techniques in blockchain?
Yes, it is possible to apply. Like only thing is, see, like they're all depending on their own requirement. So if you can come up with a new blockchain requirement, oh, that is fine. That is the basement. So on top of it, you can define your own encryption techniques to suitable. Like one of the things you can think of electronic health records, wherein like you have the like basement of the blockchain. That's fine. But you can even set the access permissions, who can access those documents and all those. That's fine. They're local to you. Like you can define. If people are interested, you can escalate to the higher issues or like scalability issues. You can address there. That's always possible. Yeah, like if you have any questions, please do write to me on my email ID and also our institute website, and then I will be happy to reply. Okay.
There's one more question by Pratibha S. Is 3 copies of data maintained in all other except Google?
Yeah, that's a minimum industry standard everyone will do, because like assume that now Amazon is having their one of the data centers and your data is stored over there, right? Unfortunately or fortunately, if it loses its content or if that data center goes down, then what the data has to, because they have to answer to the users, right? Like where is our data? Like I may request that data at any particular point of time. So it is a minimum they will keep at 3 places. So even if 1 or 2 is lost by the natural calamities or even the server failure or whatever, so that they can have a copy, so that they can access those remaining resources and get back the information.
She's again asked, is that only for data recovery?
One thing is data recovery and the other is data safety also. Not only that recovery, it is data safety. Majority of them. Safety is one thing, and the other thing is like nowadays, like there are a lot of concerns whether our country's data or the user's data can be stored at the other locations of, outside our net. So a lot of people are working on that as well. That is also another concern.
Can you able to hear me?
Yeah, I can hear you. Okay. Yeah.
And so so any every sufficient useful strip
Yeah, right. I understand that. Yeah.
even
Oh, yeah, okay. Yeah, yeah. Yeah, thank you, sir. Thank you very much. Like, it was nice to hear from you, and it was of useful. Like, I thought like mix of audience will be there, so I had kept like I had to satisfy
There's a
everyone.
judicious call.
Yeah,
Right.
that's why.
Think
Okay. Yeah, 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 yeah,
back to us.
yeah, yeah. That's what. Yeah.
It's a good session. Thank you,
Yeah,
Pavan.
thank you, sir. That's a really nice suggestion. I will take it, and we can have a forum wherein in ISIT and all. Like, there are some conferences wherein every year these kind of problems will be worked on, like mathematical aspect. Like what you told is also correct. Like, we can reduce this mathematical concept wherein we can just concentrate more on the result-oriented things, and then pose some of the problems, so that those who are interested really they can again go back to in detail, and then they can come up with this. Yeah, thank you for your suggestion.
Back
I
actually.
definitely work on. Yeah.
People see the industry benefit data science and go back to the academy. Everything to solve this problem. It will.
Yeah. Thank you, sir. Yeah. Thank you very much.
So there is one more question from
Okay.
Saru Prani. How does blockchain satisfy CAP theorem, that is consistency, availability, and partition tolerance?
Okay, I am not aware of it, exactly to prove it right now. Like, I can give you some resources, and then I will send it to you. Like, if you can write to me personally, then I will help you to get that. Okay. CAP theorem, like, which has been used in theoretical computer science for other application, which was given by a scientist by name Brewer, somewhere. It was like for the distributed data storage problem. If you can write to me, like, I can provide you more info on that. And also, like, by default, this blockchain will do that. Why? Because the consistency and availability are the two things which has to be addressed from the point of availability and the consistency. Consistency has been proved by the nature of the blockchain itself. Whereas in the problem of the availability, it has to be made ensure while creating the nodes itself by using like multiple copies, or so that the nodes will not go down, and all those things you can make sure at the availability place, or by using the suitable technology. Like, suppose say if you are using this one, like, can you go for using a non-SQL databases, or databases of which kind, or can we go it in Java, or this one, they're having the what to say high requirement application. So all those things can be addressed by how we can go for the availability. For example, if you take the Uber or the Ola, like how they have done with the Node.js, so that their systems will go negligibly down for only 1 or 2 seconds of time. All those things you can do. And then the partition tolerance, it has to be done in such a way such that, like, it will what to say it will be keeping all the things what has been mentioned in the blockchain's principles, so that it will work accordingly. Those kinds you can make sure, and then you can design such things, I feel.
This said once again, we are not partitioning the lecture.
No, ledger partitioning is not possible. Partitioning in the sense, like, what you can do is, like, it will be working as expected or not, you can do. Like, if it is any partial network failure or something is there, then still it has to work up to some extent, but you cannot add the new nodes to the network. No, it's not possible because ledger has to be like it is unique and it will not able to like what you say. As you mentioned, it is not possible to chunk into this parts
What?
by some kind of.
Instead of
You can do, but what is yeah. But the challenge is like heavy, right? Like if you want to add something, then again at the two places, entire thing has to be moved. The data transfer is the biggest challenge. Even it's not only for the blockchain. If you take even this cloud computing, like if you want to, like if you want to move a client to a new cloud, like if he's having petabytes of data, how do you send it? Because there is no migration technique from one cloud to the other. You have to download it and again upload onto the other cloud. So those challenges do exist even in the blockchain. Can we done it in a? Yeah, that can be done. Yes, that can be done. That is always possible.
Thank you.
Any other doubts or any other questions if you have?
Sir, I guess there are no more questions. No questions in the chat box as well.
Okay.
Okay.
Yeah. Okay. Thank you, ma'am. Thank you all, and have a good day, all the participants. Okay. Yeah. See you soon, some other time and some other venue. Okay. Bye. Have a nice day.
I thank Dr. Pavan Kumar C for an enlightening talk on how error correcting codes can be efficiently applied to reduce storage in blockchain and also providing research trends and applications for the same. I thank you very much for accepting our invitation and getting associated with this faculty development program, sir. It was an excellent talk, and we look forward to future such associations with you again. Thank you very much once again, sir.
Yeah, pleasure is mine, ma'am. Thank you to introducing me to the participants and also giving an opportunity to talk to all the participants. Thank you and see you all. Yeah, take care.
Yes.
Bye.
Thank you very much, sir. Thank you. Participants will meet at 12 for the next session. So that will be a session from Art of Living People, Mr. Neelakandan and Mrs. Soumya. So it is a mandate session which was actually specified by AICT for a Fit India moment. So let's all meet for the next session at 12 o'clock. Thank you very much.
What will be the test timings today, and the shared link being shared here or by email?
The agenda has been shared in the WhatsApp group. I have shared the agenda in the WhatsApp group. You can all have a look. Yes, it is at 3:10. 2:30, we just have a valediction. So at 3:10 sharp, we can start the test. Sir.
Thank you.
Actually, I'm not in the WhatsApp group. I exited by mistake. So can I?
Okay.
Ma'am, even can you guide me also about the WhatsApp group?
You want the link to the same, sir?
Yes.
Again, you want to join back? Because it is always better if you're there in the WhatsApp group, because even after the online test, we'll not be having any more meetings. So any conversation will be in the WhatsApp group regarding the certificate. So it is always better you are there in the WhatsApp group, sir. So I'll just share the link in the chat window here itself now. Please rejoin back to the WhatsApp group.
Ma'am,
okay.
I'm Chetan here. Ma'am, I am also not having any WhatsApp group.
Oh, yeah, please join the WhatsApp group. I'll share the link now.
Sending me the link, please.
Here in the chat box right now. I'll share it in the chat box right now. Because after 4 o'clock, there won't be any meetings scheduled anymore. So if you want to interact with us, WhatsApp is the only option. So regarding the certificates, because that will be released late, it will take another 2-3 days for the AICTU to release the certificates. So till then, you should be in touch with us. It's the only option is either through mail or WhatsApp. Yeah, so better you are there in the WhatsApp.
I have to join. There will be a session for the exam also, no?
Yes. We'll be sharing the link in the group, Google Classroom, and in the chat window also here.
Okay.
Share the link to the WhatsApp group, please.
1 minute.
Yeah. Yeah, I've shared the link. Those who are not there, please do join the WhatsApp group.
Thank you, ma'am.
Yeah. Thank you all. We'll meet at 12. Thank you. Yeah.